On the mathematics of radioactive decay. Hopefully you're aware that whenever we're graphing, say, the activity or the number of unstable nuclei in a sample, we tend to get curves like this, and this is what we often refer to as exponential decay. What we're going to do is we're going to just look at the maths of radioactive decay. We're going to get some definitions down, and then we're going to see where these curves actually come from and what the parameters mean in the kind of mathematical description of those. So I hope you enjoy. Let's start from the beginning. To get that kind of exponential shape, we need to start with two very important equations. The first one there is our A is equal to minus dn by dt, and second one here is A is equal to lambda times n. Let's define a few things here. Okay, first things first. Activity A is the rate of decay of the unstable nuclei n. So you can see n comes up in both of our equations. We've got on the left activity equals the negative of the rate of change of the number of unstable nuclei with time, and also activity is equal to some constant lambda times the number of unstable nuclei n. That constant lambda is referred to as the decay constant, and it is the probability that the nucleus will decay per unit time. What we're really saying there in that second equation is that the more nuclei I have, the more decays I expect. And that makes sense because obviously if we have more nuclei, then the more of them are going to break apart than if we have a smaller sample. The key to doing this then is to equate the two. Obviously we've got A in both equations, and so therefore we can take the two together to say that minus dn by dt is equal to lambda times n. After that we have to do a bit of calculus. Okay, if we just shift things around, you should be able to see that if we put dn over n and lambda dt and put the negative on the right hand side, well, if that's true, then the integrals must be the same here as well. Those of you who are maths fans will be aware that the left hand integral is just the integral of 1 over x dx, which gives the natural log of x, or in this case n. And on the right hand side we've got a constant number integrated with respect to t, which gives us minus lambda times t plus some a. Now I'm realizing now that's a bad choice of letter there. This a is just simply a constant. If we want to then simplify this equation, we can say take e to the power of each side, so e to the power of log of n is equal to e to the minus lambda t plus some constant a, which we can then rearrange as a function of time. N as a function of time is equal to some n0, that's a constant, times e to the minus lambda t. And this is the point at which we've got our exponential decay. Now it's important to remember that you're not going to be necessarily tested on this kind of maths, okay? However, it's good to know where this kind of stuff comes from, and also you need to be able to manipulate the equation as we're going to do in the next slide. Okay, let's have a look at how this relates to something like half-life. And again, we've just put my equation that we've derived up there. N as a function of t is n0 e to the minus lambda t, where n0 is the number of undecayed atoms at, say, time equal to 0. We defined previously half-life as the time it takes for the number of undecayed nuclei to decay by a factor of a half. And so therefore, at some time equal to t half being the half-life, the ratio of the number of undecayed nuclei to the original number is going to be 1 over 2. The result of this is that e to the minus lambda t times t half here being a signifier, not a power, is just going to be equal to 1 divided by 2. And so therefore, if I take the log of both sides again, I'm going to have minus lambda t half, I've just taken the log of the left-hand side, is equal to natural log of 1 over 2. And again, if we take that number into a decimal, it's 0.693. And what this says is that the relationship between the half-life and the decay constant is inverse. In other words, As lambda gets bigger, the half-life gets smaller. As lambda gets smaller, the half-life gets bigger. And we can understand this in this way, that we said before our decay constant was the probability of decay. Well, if we've got a high probability of decay, what this then means is it's very likely for that number n to go down very, very quickly. And as a result, we're going to have a short half-life. Lambda is high, t half is small. Conversely, if we've got a very low lambda, that means there's a low probability. It means it's going to, the number of nuclei, is going to go down very, very slowly. Okay, and therefore we're going to have a short a long half-life. Okay, so really here we're seeing the kind of the link between those two parameters, the half-life and the decay constant multiply together each time to produce a constant number, and that constant number happens to be negative log of a half, i.e. log of 2. Okay, take some time to look over those equations. Very quick bit of maths there. I hope you have some questions, and if you do, please chuck them over to me. I'd be only too willing to help you. Thanks for watching.